Hello, everyone. Welcome to this webinar from Varus Engineering. It's 1 o'clock here on the East Coast, but we'll give people another minute to join. My name is Sean Teller, and I'll be giving the webinar today on Polymer from test data to accurate simulation, polymer material model calibration for Ansys Mechanical. We'll just give people one more minute, then we'll get started. All right, we will get started. So if you have any questions, go ahead and please put them in the chat or the Q&A. I'll try to monitor that throughout this webinar. And if I don't catch it at the time, I'll get to it at the end. You should all be able to see my screen. So as I said, I'm Sean Teller from Varus Engineering. I'm a principal and partner here. And today I'm going to be talking about how you can, the types of models that are available in Ansys Mechanical to capture the behavior of polymer materials. So first, a little bit about Varus. So we are a small engineering consulting company located west of Boston in Needham, Massachusetts, and we've been around for about 20 years. Currently at 12 technical staff, highly skewed towards PhDs, and we have a few more people joining us in the fall that will help us on there. We are software agnostic. We like to say we're cross-platform, so we work in Abacus, Ansys, COMSOL, LS Dyna, as well as kind of other niche codes when needed. But today we're going to be talking about some Ansys Mechanical work. And then we work in multiple different areas. So we do a lot of simulation analysis, we do a lot of failure analysis, and we do a lot of material testing and modeling for our clients. So over on the right, you can see a bit of that breakdown, where kind of over here, you have what we're going to be talking about today: material testing and modeling, nonlinear solid mechanics. Not really materials engineering, though maybe it falls into that category. Sometimes we also do product testing and failure analysis. and those are all areas that I work in, and then these other kind of areas are areas that other people work in the firm. That's other types of multi-physics simulation. So it's a heat transfer, low frequency EM, fluid mechanics and turbulence, fluid structure interaction, ECAM, reacting flows, all those types of things. To talk a little bit about our test lab, we are different than many other test labs that are out there. Our test lab really came from the fact that we were modeling polymers, and that we needed test data to do that, and we had been using outside vendors to do that for a while. And then at one point we decided we wanted to take that in-house, and we've been doing that since then. So our test lab is completely focused on getting test data for FEA and CAE engineers. And many times we have FEA and CA engineers who also run those tests. So they understand the type of questions and thoughts that you might be having. And so all of that data is used to inform finite element models in some way. We do try to focus on the complex nonlinear phenomenon, and we're not going to do 100 ASTM 1, 2, 3, 4 tests. We're going to custom design a test program for your material in your application to get a material model that will accurately capture the time or temperature dependent response of your material, so you can include that in your simulation. And just a little bit more, this is in our series of free webinars. So I've listed the next 3 that are coming up. There's one in August that I will be giving actually with one of my colleagues, Scott Grindy, on thermoforming applications, materials characterization, material modeling, and simulation for better process outcomes. There's another one in August from one of my colleagues, Joe Barakat, on CFD modeling for particle technology and process development. And then my colleague Mark is going to be giving one on adhesive testing and material model calibration for FEA of bonded joints in early September. On top of that, those are our free webinars. On top of that, we also do paid training courses. So I do training on material testing and modeling. And we have the advanced testing course coming up in September. That is online, 4 2-hour sessions in 1 week where we go through a whole lot of material, including a lot. We'll go into in-depth some things that you might see or models you hear about today. So I highly recommend it. We also do I wouldn't call it an intro class, but a non-advanced class, typically in the spring. And we do an in-person class as well, which we're currently trying to schedule for this fall. So if you have any interest in that in-person course, please reach out to me and I can try to include you in that scheduling. But you can always reach out to us at contact@verus.com or seminars@verus.com, and we can notify you when we have new webinars scheduled or new seminars scheduled. Just to take a step back, I kind of mentioned this, but I wanted to talk about what we mean by material modeling and that material modeling workflow. And so this is a graphic we put together to describe that. Hopefully that you are familiar with it because you're here. But over on the left, you see that we have test data that we're capturing and collecting in our lab. You see some tensile tests there or a compression test on there. So that's your material and your form factor that we're testing. And then we get that data, and the solid lines are the data, and the dashed lines here are our material model prediction. You can see this one we've done at multiple rates. Then we create a material card, and you can see there we've listed all sorts of finite element codes we work with. But in this case, we're interested today talking just about Ansys. And then we like to do material model validation. So this is something where you take a more complex geometry, run a test. We can't write down the stress or the strain or the force. And we use that advanced material model that we've developed to simulate it and compare our simulation to the experiment. This is an example that we did years ago on a 3D printed lattice structure that worked very well. You see we've got great agreement between those two. So that's the process that we're going to talk about today. But first, I want to do a little bit here. We're going to try something a little bit new for me. So hopefully this goes off without a hitch. But material modeling, how do I simulate this? So we're going to talk. So I had some questions here, and I'm going to launch a poll. And the first one is going to be, what type of material models have you worked with in the past? So hopefully you are seeing a poll up on your screen. If you could check a box and hit submit, that would be great. I've listed these in kind of least to most complex. So you only need to choose one, and the most complex one is the one you've used. It'd be great to see those results, to see what people here have done. So we got a couple of people who said they've done hyperelastic. We've got some people who've gone all the way to nonlinear viscoelastic, viscoplastic, some linear viscoelasticity. We got some people doing other. Other I generally think of as like a user material or something more complex. We have some people who've worked on elastic plastic. So it looks like everyone's gotten beyond elastic only. I would say linear viscoelastic is more complex than hyperelastic. Someone just asked that question because linear viscoelasticity can be a misnomer because you usually have some nonlinear effects in there, the linear response to the viscoelasticity. So it looks like the majority of people or the plurality of people have gotten to linear viscoelasticity. But there's a good spread there. So that's great. Thank you for responding to that. We've got one more poll here, and here's a little bit some market research for me, which is, where do you get your test data from? So that should be up there as well. We've got a couple options there: external labs, internal labs. You are the test lab, a material supplier. There's an extra one in there, both internal and external labs. So maybe you do a mixture, or maybe you never get test data, and your answer is, what is the test data? So I'm going to choose I am the test lab. Let's see what people are going there. Okay, so we've got looks like a pretty good mix. We've got some people who are external labs only, some people internal labs only, some people who do both, a little bit from the material supplier. but nobody has chosen what test data. So that is great. That means that, everybody here has gotten some test data, has communicated to their organization the importance of test data when you're trying to simulate these complex materials. So that's really good that you've been able to get your organization to support you in that way and get that data. So thank you for participating there. This is this is always interesting for me, and that went without off without a hitch actually. So something went right in Microsoft Teams. So that's great. So let's move on here. So before we even get into kind of what these material models are and what they can predict, I want to talk about just what they are and how I characterize these, because it might not match with kind of what you were thinking. So I've broken these broadly down into 5 categories of material models that are available in Ansys, and we're going to go through examples of all of these today. So there's the elastic model, so isotropic elasticity, or maybe anisotropic elasticity. And that's really just Hooke's law. We also have elastic plastic models in Ansys that's called, bilinear plasticity, multilinear isotropic plasticity, kinematic hardening plasticity, and you can mix those together as well. There's hyperelastic models. I've listed 4 there. Ansys has 8 or 10 off the top of my head. So there's a whole lot you can get into there, but these are kind of a next level up. And then we have linear viscoelasticity, which as someone kind of brought up. What does the linear mean? And we'll talk about that in a little bit. And then at the end, we've got nonlinear viscoelasticity or viscoplasticity. I'm lumping those into one because I have a certain way I define it. It doesn't necessarily match how other people define it, and it's a little bit of a gray area, I think. But as we go through that on the right, with what it captures, a linear elastic or an elastic response is just Hooke's law. That's what we learned in our beam bending 101 in undergraduate, and it's very simple. Next, we have elastic plastic. So there we're starting to get into some non-linearity, and we're getting plasticity, permanent deformation, that when you remove the load, you still have some deformation. You can get some rate effects there. We're going to be talking about rate effects throughout today. So you can get those rate effects with some options that take a little more complexity, but you can capture that. If we move on to hyperelasticity, we're getting nonlinear stress strain. We can get to very large strains and have a computationally robust model. And we can get some pressure dependence in there as well. Pressure dependence in this case means that you get a different response in tension versus compression versus shear and other loading modes, which can be very important for some elastomers. Linear viscoelasticity. Again, this is really the first one where I think we're looking at something that was used to develop and capture the response of polymer materials, and get those time-dependent effects that polymers really show. So we get nonlinear stress strain when you have a hyperelastic model in there, and you get things like hysteresis, stress relaxation, or creep, and capture those in those models. And then that last one, those nonlinear viscoelastic, viscoplastic models. All right, this is kind of the full boat. We're getting nonlinear stress versus strain, plasticity, rate dependence, hysteresis, relaxation, creep, all those sorts of things. So we're capturing them all, and really this is the state of the art in there. I see a couple questions popped up. Multiple choice, yeah, okay. Yes, Ansys just purchased Bergstrom Boyce on Calibration. Yeah, that was a few years ago. You are correct. So I talked about what they can do, but what about what these things miss? Well, the first is that a linear elastic model misses everything. It really doesn't capture too much, and we're going to quickly get beyond that, and hopefully I show you that quickly. Elastic plastic. Typically, you're going to miss rate dependence. Again, you can add some rate dependent options. I think that starts to be a lot of work for not a lot of gain, and I'd rather start to use some of the other models that we'll talk about today. And you also miss any of that pressure dependence. This is also going to be very poor at anything like an elastomer, a rubber, a foam. They just are going to predict the wrong thing when you get any sort of unloading, so I don't recommend it at all. Hyperelastic models, You're going to miss hysteresis, creep, relaxation, and unless you add a creep model in there, which or the Mullins damage model, which we'll talk about later today. Linear viscoelasticity, that's where you really start to get a lot of those effects in there. But what you start to miss is that permanent deformation or plasticity. Those linear elastic models, as you pull them and release, they're going to eventually come back to where they started, and that's not always what we see. And then for the for the built-in models for the Bergstrom Boyce, so the 3 network model, what are we missing? We're missing some anisotropy. Those models, those 2 listed there, don't have any anisotropy that you can use with them. That's a little more niche, but it's definitely something that we run into. We work with a lot of fiber-filled materials. Those are anisotropic, so you want to be able to capture that. And so that's something else that we can talk about. So there's one question there. What about polymer composites and anisotropy combined with these nonlinear effects? Is this still considered a gray area? That's a good question. I'm not as familiar with, if you're talking about long fiber composites, I'm not as familiar with material models for those. If you're talking about like short fiber composites, like glass fiber, short glass fiber filled polycarbonate or something like that, what I'd say is that most of the, a little careful here because I always get myself in trouble. Most built-in finite element codes just don't have anything that can get a nonlinear stress strain response, and with rate dependence and anisotropy. So it becomes difficult. Some codes you can get to, and I think Ansys is one of them. You can go back to an elastic plastic model that you see over here. If you go back to this elastic plastic model, there's some anisotropic yield behaviors and anisotropic elastic behavior that you can get in there, but you're going to lose a lot as you go to these that coming back from these. So it's a little bit of a trade-off. Someone asked, where do 3D printed polymers sit? I think that the same discussion just applies. We have anisotropy, so you might have to do a trade-off between, can I get the complex nonlinearities and the complex time dependence with these models, but I can't get the anisotropy. I can get the anisotropy here, but I'm not going to get that complex time dependence or cyclic loading. So sometimes it's a little bit of a trade-off. You can always do a user material model, but that's obviously a lot more work up front, but it can be very fruitful to do that. And kind of, I'm going to bang this drum because I do this with my engineers and everyone I work with here. If you are, you need to be an expert in your finite element codes manual, and you need to know where to find things. The AI and LLM solutions are great for helping us find some things. The search engines are great, but nothing beats it if you know where the material models are in the Ansys manual. You can just go there and find what you need right away and go from there. And I find that that's even faster. The Ansys model is actually pretty good. I'd say it's tied with Abacus for kind of quality of the manual, where it goes into everything that's in there. So if you're working with the model pretty extensively, I would definitely read that section of the manual to really understand what's going on there. You can see that there's all sorts of nonlinear material parameters. We're not talking about all of them today. We're going to talk about some rate independent plasticity, some hyperelasticity, some viscoelasticity, and that's really it in terms of all these different models, right? So there's a whole lot that we're missing that it can capture. So I would definitely make sure that you understand the manual, where these things are being used, and what goes into it. But let's go back to the beginning. Linear elasticity. Linear elasticity is great because you need 2 parameters. A lot of times we can get that from a spec sheet. The quality of that might be questionable, but we get those and then we can just run. The equations are shown there over on the right, which I hope we're all familiar with. But you have Young's modulus and Poisson's ratio, and then the others fall out of there. And there's a Wikipedia page if you don't know, and I can use that. So what does this mean for us? But this is an example I like to show on an HDPE material for tension that we did in our data, and I'm just showing this up to 5% strain. I believe we have this data for another example later in the webinar here. But I think this shows really good where some people are like, I'm at 1% strain, I'm at 2% strain. Why do I need more than linear elasticity? Well, I think this shows it. So first, we did these tests at two different rates. So the red curve is at 0.1 strain per second. So it goes to 10% strain in 1 second. Or the blue one is at 0.001 strain per second. So it goes to 0.1% strain in 1 second. So very different rates. I would actually consider both of these quasi-static, but you can see that you're getting a very different response. Here at 1% strain, the test data is, at the higher rate is 50% higher than you had at the low rate. So how do we choose what our modulus is? If I choose the tangent modulus to both of these curves really at zero strain, I might get this red line. If I want to choose like a secant modulus to this blue one to 1% strain or something like that, I get this blue line here. But that's a pretty big difference. If you look, one of those is 1,000 MPa, the other one is 1,630 MPa. So a 60% increase in the stiffness, right? So that's just huge. So the question is, can your model deal with the 60% error and you still be comfortable with that? And I'd say no. And that's just an error between these two. It doesn't actually count the error to the actual test data. Maybe the majority of your application is below 1%, but you've got, a moderate part of your part that's maybe at 2% strain. We're going to predict a much higher stress than you would here. You should be at 14 MPa, but you're predicting 20 MPa, right? So that's very, so you can have a lot of error even at low rates and low strains for some of these polymers. So it's something that we really want to keep in mind. So when is linear elasticity good? Not very often at all. So we're not going to spend any more time talking about linear elasticity. And I switched up the order here, I think, from what I put up top. But I'm going to talk about hyperelastic models. And these are really our first foray into some nonlinearity and what that can do for us. Again, without going into a whole lot of details on the math behind that, because we just don't have the time, we define hyperelastic models in terms of this, a strain energy density U. So when you look at the Ansys model, there's a screenshot there showing all the models there, which they show 12 different models there. It defines this U value, gives you a strain energy density, either in terms of the principal stretches or the first and second strain invariant, first, second, and third strain invariant. That's what I1, I2, and J are. And so that's what the strain energy density is, and then you calculate the stress from these equations. So they look a little complex, but they're fairly simple, and that's kind of the math behind there. But one thing to keep in mind is, right, they're hyperelastic models. That means they're elastic. They store all their energy, and no matter what you do, you let go, they're going to come back to where they were. So I think that's something we want to keep in the back of their mind. If we look at all this, the models that I use most, if we're talking about hyperelasticity, is Yo hyperelasticity. I also like Aruda-Boyce a lot, although it's not as flexible as Yo. And those are the two I use the most. I use Ogden Hyperfoam fairly often as well. That is, as you might guess, for a foam material. So I've calibrated some of this test data. I've calibrated some of these models to this test data. So in this case, we took a TPE material, which is a thermoplastic elastomer material. This one's called Sansoprene. A TPE material, which is somewhere between an elastomer and a thermoplastic. It's because actually those two components are mixed together. I calibrated a material model, which is this dash line. You can see I call that out as the simulation down here. And this matches really well. I've got an error of 3.2%. If you want to nitpick, we need to be a little bit stiffer here. But sometimes this is kind of as good as we can get to capture the nonlinearity over this entire range, right? We're almost to 200% strain. So you might think, Sean, this is great. Why are you, giving caveats, anything like that? Why do we need to go any further? Well, right, we then took that same material, we tested at 3 different strain rates from 0.001 to 0.1, right? And this model predicts the same thing. There's no rate dependence, right? So you see that, brownish purplish curve, right? And all the material models are just right. Predictions are right on top of each other. You can't even see the three curves because they're right on top of each other. So this is something that we're missing. And maybe you're saying, Sean, I'm okay with this level of error, and maybe you are, and I'm not going to fault you for that, because we always need to make sure our models match the complexity required and the certainty we have. And oftentimes I'll start with a model like this to get the model running, understand, and then I can build in complexity if I need to. But there are other problems with this model. Not only can it not capture this rate dependence, but it doesn't capture any sort of cyclic response. So I took that Yo model, and I have a cyclic type of test data here. So maybe in a couple of slides we'll see a little bit more of this. But I loaded this up to 25% strain, and then I unloaded, and then I reloaded the 25% strain 5 times. And then I did that at 50% strain, and I did that 5 times. Then I went to 75% strain and did that 5 times. And then I went to 175% strain and unloaded. Right, so I simulated that entire thing, and you just see this solid green line because it doesn't capture any of that hysteresis. It's one-to-one. You give it the strain, you get the stress. There's no time dependence, nothing like that. So how can you capture that? So there's something called the Ogden-Roxburgh-Mullins effect, or Mullins damage, is what I like to call it instead of the Mullins effect. It's a way to modify these hyperelastic models to capture that hysteresis during that unloading. This model has been around for a while and is very good. It was developed specifically to talk about filled elastomers and carbon black that's in elastomers. And to understand that behavior and model that behavior. The way this works is that it multiplicatively modifies the stress response with the damage parameter eta. So I put the kind of how the stress gets changed there, and then I put how the eta parameter is calculated. It has to do with the internal strain energy density, a maximum, and 3 parameters, R, M, and beta, or B. Right, and this model was developed to answer the question that we just saw on the previous slide, what you see over here. How can I capture this hysteretic unloading? And the model that they came up with this Mullins damage. So what does that do for us in that TPE data? So here I've calibrated that Mullins damage to that same test. And you see I'm capturing it much better, right? So I come up here. You see when I unload down in this area right here, I'm capturing that response better. I'm better following those curves. I don't get quite the hysteresis on each one of those reloads that I might want, but I'm matching that shape a lot better. And I'm not just following the path that I loaded to. And you see that kind of happens on each one as I come here to this third one, and even up here to 175% strain, I'm capturing that significantly better. So I've made a lot of progress with capturing that, and we can get this response a lot better. So what do we do? The other thing that I wanted to look at is one of the characteristics of Mullins damage is that under repeated loading, your stress changes. So here I'm plotting that stress versus time for the actual test that we did, where we loaded up, 5 times that 25% strain. And as you look at this, you can see that you're getting a not a relaxation. You're getting a reduction in stress. And by the time you get to the 5th cycle here for this particular material, it's different for all materials, you've kind of plateaued, and you see that repeated over and over again, where you're kind of plateauing. You can see the model does that in some sense as well. We're a little too soft here, but we're matching these other ones really well. So wanted to look at kind of what the difference is between those different models. So in the kind of medium green, we show the cyclic tension data. The dark dashed line is our Yo plus Mullins simulation, and that very light line is the Yo only simulation. So you can see, here's a good visual way to see the difference that Mullins gives us, where it's getting that unloading effect much better and getting us much closer. And really, this is there's so little computational cost to add the Mullins damage that if you need it, there's no reason not to if you can get the parameters for it. We quickly went through hyperelastic models there and talked a little about hyperelasticity plus Mullins. So next I'm going to talk about elastic plastic models and really try to answer what can metal plasticity do for us. My answer is I don't really like it too much. But you'll hear me refer to these things as J2 plasticity models. If you aren't familiar, J2 plasticity models, or you might also call metal plasticity models, really they mean that they're isochoric during plasticity, and that falls out of metal plasticity, where this deformation is due to grain boundary behavior and dislocation motion, which themselves are inherently volume conserving. So that's how plasticity was developed. There's all sorts of other things that kind of go into it. We could talk about the different types of yield surfaces, whether you want von Mises yield curve, a Tresca yield curve, something else that's going on there. There are a lot of ways that we could talk about that. But as we go through this, there are other questions you could ask. Do you want isotropic hardening or kinematic hardening, and what that means for your model? Isotropic hardening means that if you get yield and tension, the yield surface is increased in compression as well. Whereas kinematic hardening, instead of expanding the entire yield surface, you shift the yield surface. So then you might have a different yield stress in compression versus tension. But essentially, we define that yield surface as some sort of function of some internal variables and go from there. So I see. So someone asked, how do you determine the value needed for the Mullins effect? There are some ways that you can kind of look at those responses and calculate the strain energy density and get some at least approximations of those parameters by going through some pretty heavy analytical or moderately heavy analytical math. But the true answer is material model calibration. As someone had mentioned, there's various programs to do that. Ansys has a program called Calibration, which was developed here at Veris Engineering and was spun off years ago, but is now a part of Ansys. So that's really a great way to do that. You can do it yourself as well. Either if you don't have the Calibration license, you can use optimization routines like OptiSlang in Ansys Mechanical, or you can write your own codes. Where you basically program in your material model and find those parameters. And I've done a mix of all of those things to calibrate material models. They all have their advantages and disadvantages. There's another question here. It says, for elastomers operating at temperatures ranging from 100 C down to 5 C, how should temperature effects be captured in a hyperelastic model? So there are a couple of ways to do that in Ansys. One is to use a time temperature superposition principles, where you have parameters for the WLF or the Arrhenius relationship. So that's one way. That can be a little more maybe obtuse or difficult to do. The other thing you can do is you can calibrate a material model at the different temperatures that you have that test data at, and then tell Ansys that that's what that temperature dependence is, and it will linearly interpolate in between there. Another question here. By calibrating the model, do you mean some other intervention to match the test data other than just applying the model and running the solution? Well, by calibrating the model, it's how do you find the 10 constants that the material model needs to match your test data. A Yo model has, linear elasticity has two parameters, Young's modulus and a Poisson's ratio. We can get those analytically from a test. If you start to talk about a Neo-Hookean model, again, you need a bulk modulus and a shear modulus. You can get those, but then you don't have a lot of other control. As you increase complexity, you have 10, 12, 15 or more parameters. How do you find each one of those parameters? And the way we do it is essentially we do a single element, finite element simulation with a candidate material. And then from that, we compare that to our test data, and then we do some nonlinear optimization on the material parameters, and we run that hundreds to thousands of times. All right, I'm going to come back here to elastic plastic models. So we talked about that introduction. So here I've calibrated an isotropic hardening, multilinear isotropic hardening, or MESO model in Ansys parlance, to that HDPE material. Overall, the model captures the results well. we could get things a little bit smoother, but I didn't want to spend a lot of time on it because there is some you know essentially I don't use these models often, so I don't want to spend too much time calibrating them because they have a lot of downsides. So what are those downsides? You could say this looks really good, Sean. You get to 50% strain and compression and 20% strain and tension with very little error. Why are you poo-pooing this? One of them is that rate dependence becomes a little more difficult. So here we're comparing something at 0.1 strain per second to something at 100 strain per second. And the normal elastic plastic model doesn't capture that. You can add things with the Prasina and Pierce options in Ansys to get some rate dependence. But again, I think you're putting a lot more effort into a model that's going to have issues anyway. Because the other thing that this model does very poorly is cyclic loading of a polymer. So it's that same HDPE model, that same HDPE material, and the red curve we've done at a different strain rate, and we've done some unloading where we went to 5% strain, we did some relaxation unload, and then we went to 15 and 30 or 35. I did that same thing. And the red line is a prediction there. And this is what metal plasticity would predict. Right? We have a very stiff unloading response that matches that initial slope. So we get to this very high compressive stress, and actually it looks like we yield the material in compression by going there. Yeah, and we do because we increase the yield stress on that reversal, right? So this is, anything where we have this relaxation or unloading, this model is going to be way too stiff and have a lot of problems. So I'm going to keep moving to make sure we can get through everything here. We got about 25 minutes left. So we're going to talk about rate dependence and what that means. I see a comment here about the Bauschner effect. I believe the Bauschner effect is a metal plasticity model. So again, I try to move beyond all these metal models. I want to get into the models with that are made for polymers, because they're going to do a much better job of capturing these things. I see a couple other questions that I'll come back to. So linear viscoelasticity. So this is our first model that I would say was developed from the ground up to incorporate time dependence and captures increasing or decreasing increasing stiffness with the applied rate, as well as creep and relaxation. So we get this by just kind of adding one effect. The models are generally pretty efficient. You can make them inefficient if you want, but generally they're pretty efficient. And I like to pair them with hyperelastic models for the elastic portion of the model. So that's where I kind of made a comment earlier that is called linear viscoelasticity, but it has nonlinearity in there because the linear part applies to the viscoelasticity, the rate dependence. That is linear, but you can have a nonlinear stress strain response. So the most common way that this is implemented, and this is what we're going to talk about here for Ansys, is a Prony series where you can have an arbitrary number of elements that all have elastic elements in a dashpot, nonlinear elastic springs in that dashpot, and then we have some elastic element down here that gives us the stiffness, the long-term stiffness of the material. And so for each one of these networks that we have in there, we have a unique relative strength. It doesn't have to be unique; they can be repeated, but generally they are, and a relaxation time. So for each network that we add, we have 2 more parameters that we're going to need to optimize. So what can it do for us? So here's that same Santoprene data on that rate dependent. So I've taken a Yo model with the Prony series and I've calibrated it here. And you can see that we're getting difference between all these rate across this, across the entire strain range from 0% strain all the way up here to 150% strain. We're seeing a difference in the stiffness. And we're capturing that response really well. Basically, as well as the Yo model can capture that shape. So we're really getting a good rate-dependent model for the test data in there, and we can be very happy with that. It can also get that stress relaxation and creep. I took that same model to that same Mullins data, and I'm just showing 5 cycles here. But we get that rate dependence where the stiffness increases. And then we see a stress relaxation. And now we could definitely use some more stress relaxation here, but we see that we are getting stress relaxation. Here, maybe we're at, 10 or 12% stress relaxation from peak to the trough here in about 30 seconds. Whereas here, we're maybe only getting 2 or 5%. So we don't have quite enough, but we are getting relaxation. We get some some creep as well. So that can be really great for us to capture that type of dependence. As we kind of saw earlier, actually the LVE model doesn't do a great job capturing the unloading, which you might be able to tell by here, by the space between those lines there, just because that effect really needs to be captured. Part of that unloading effect really needs to be captured with the Mullins damage, and that is something we can do. We can add Yo plus Mullins plus viscoelasticity to really get a lot more going on and capture that response. But I always like to caution people to be careful about using Prony series because you can sometimes get yourself in trouble. So this is an example I put together. This is on some DMA data or data from a dynamic mechanical analyzer. And on this, we've done a lot of work to get X should be time there. Yeah, you are correct. We've done a lot of work and analysis to get a large frequency range where we've over 14 decades of frequency or strain rate here, right? So we can see that this particular material stiffens pretty significantly, right? That's almost 4 orders of magnitude stiffness change as it goes through the frequency. And we also have a storage and a loss modulus. And these are viscoelastic terms and tell us how much energy is stored in the material. That red line or the loss modulus tells us how much is dissipated. So you can see here I've calibrated a model that matches pretty well. Up here at the highest frequencies, maybe you say, Sean, you can do a little more work here. You got some lumps in your curve that don't quite match, and maybe down here at 10 to the minus second. But overall, this captures it very, very well. So we know a model can do this. But let's take a step back and say, okay, what's a danger with an LVE model? So I've taken that same data, I've truncated it to a much smaller frequency range over just 5 decades of frequency, up to about 100 hertz, and I calibrated a model. Maybe this could be a little bit better, but overall this is good. It's capturing kind of the trends. These things could be shifted up or down, but overall, I'm pretty happy with this. So maybe I use this model, I run, I get some results, and things look good, and then I manufacture whatever I'm manufacturing, and I start to have issues and I don't understand why. Well, we need to understand what goes into this Prony series, and in this example, we only calibrated it to data from 10 to the minus third to 10 to the second hertz. So if we then take that same model compared to the actual material response, but then simulate at those higher frequencies, we get what we have here, where the storage modulus, that elastic modulus there, just plateaus, and we just have the same stiffness, even though that material is stiffened by another 2 or 3 orders of magnitude beyond there. Our model doesn't capture that because we didn't have that information when we captured it. Similarly, the loss modulus essentially drops to 0. We're at 10 to the minus 4th here, right? So there's effectively no dissipation, no damping, anything like that. So you really want to be careful when you're using that Prony series because that could cause some issues for you. I'm going to come back to the questions at the end to make sure that I get through all of this. So next we're going to talk about nonlinear viscoelasticity and viscoplasticity, and we're going to talk about 2 different material models. So the first one is the Bergstrom-Boyce model, or the BB model. This was developed by Jorgen Bergstrom when he was getting his PhD with Mary Boyce at MIT, and his thesis says, how can we capture this material behavior? So this is some compression data, shows some rate dependence, shows some stair-step tests here where you see some relaxation and unloading. So how can we capture the rate dependence, that relaxation with one model? So he put together this form. So it's a 2-network model that has some Arruda-Boyce or 8-chain hyperelastic elements and what's called a Bergstrom-Boyce flow elements. And there are 8 total model parameters for you to calibrate to this model. We're not going to go through those equations just because we don't have the time today. But the answer is, because this was Jorgen's thesis, obviously, it matches pretty well. right? So you can see these are a calibrated material response where we're getting, we're capturing some rate dependence. So the green versus the blue and the red is a little bit different, and we're getting a really good response there. There is a little bit of oddness going on, which we'll talk about in the next couple of slides. So breaking that down into just one of those, you can see that we're capturing this pretty well, but there is, a little bit down here at the small strains where we're a little too stiff, right? You see that we're stiff instantly, and then we kind of soften out. That has to do with the form here. I like to call this a viscoplastic model, even though it's referred to as viscoelasticity, because essentially this is some yield-like behavior right here, and some of it can be permanent. So some of it is permanent. So you need to be careful about that. That's kind of a downside to the model, but other than what's happening there at those very small strains, it's capturing this response very well. Not quite stiff enough here, getting the unloading shape very well. And again, if we look at that stair step and stress versus time, and zoom in on one of those boxes, you can see that we're getting that relaxation pretty well. We're getting the magnitude here very well. There's a little bit of an offset between these two, but we're getting that magnitude well. And we're getting that at all, 4 or 5 of those strain levels that we tested at. So we're capturing that response well. So that can be very good for capturing elastomer responses. And the next one I want to go to is the 3-network model. And I see I've got a little bit of a typo in this slide. I apologize for that. So this is a model that was developed for ultra-high molecular weight polyethylene by Jorgen when he was and the paper was published when he was here at Verisk Engineering. And it's very simply named, I would say. There are 3 networks, so it's called the 3-network model. But and it was developed for ultra-high molecular weight polyethylene, but is very good for capturing all sorts of thermoplastics, TPEs, and even elastomers. Though sometimes it can be a little bit of overkill. The model has 13 parameters when you're temperature independent, and 4 more when it uses some built-in temperature dependence. And in my opinion, it's one of, if not the most advanced built-in material model available in commercial finite element codes. The most interesting thing about this is a stiffness evolution term, which dictates how one of the 3 networks, network B, how the stiffness of that network evolves and changes based on the deformation in network A. And so it starts with an initial stiffness, mu bi, and evolves to a final value, mu bf. And this really is some sort of damage modeling or softening model, and it opens up a lot of capabilities and physics that we can capture. So I've shown kind of what those changes in the mu bf value are. So everything else about these 3 models are the same. This is simulating a tension test. So if I don't have that feature active by having no mu bf evolution, you kind of just see almost like a trilinear curve, right? There's a line here. If you look closely, you can see a little bit of a kink in that line, and then there's one final kink, and there's some not quite straight line there, but that's that. Once I change that mu bf and go to what I'd call a moderate level, you can see there that we've got some softening, and we've kind of rounded out that yield. And then when I go to a very low BF, you can see I get an extreme amount of softening behavior and nonlinearity, and then it stiffens back up. So you can get a lot of effects, and get a lot of physics in there. It can be a very interesting model. But what can we do with that in practice? So here I've shown the response for tension tests at 3 different rates, up to an impact rate of 500 strain per second. And overall, and this is on a Sikaloy material, which is a mixed PCABS, an engineering grade material for high performance applications. This matches fairly well. There are some issues with it. If you look down here, it captures the yield stress here as well. It doesn't get as much softening as it should. And you might say, Sean, you just showed me it can capture that softening. I'll talk about that in a second. Here we're at a little bit low of a yield stress. So depending on your application, you might definitely want to tweak this. But for going over 6 or 7 decades, this is a good start here. And you can see that it's capturing that unloading response a lot better. And here up here at 50% strain, it really captures that unloading well. not as good at the really small strains. We see a lot of that stiff unloading that we saw with the metal plasticity, but this is, orders of magnitude better than what we see there. So the reason we're having problems capturing that post-yield softening is that mu bf parameter captures both what happens to the post-yield softening, this drop here, this potential necking that we get, and then here we get but it also dictates what happens during the unloading. So we're trying to capture two effects that are related but are different with one term in there. And so that's something that we might want to improve upon. There are more advanced models, but they aren't really built into finite element codes. You need to do something with user materials. So it's a little bit out of scope for today. But that's that. The three network model also captures stress relaxation. So you can see here that, in that one test, you see that we're capturing the relaxation well. Again, it's a little soft at that first one, but overall, we're capturing the amount of relaxation fairly well over the 60-second relaxation holds that we did in this test. So, I need to make a manager chart with red, green, and orange on here. And I tried to give thumbs up as well and thumbs down and some rotation there. So I don't know if that makes it a little easier to understand or a little bit harder to understand. But I'm going to try to leave it here and summarize this in just 1 or 2 minutes and get back to the questions. So elastic models, when should we use that? Almost never. I'd say SWAGs is where you want to use that, which is a fancy acronym to say it's a guess, because it's not very accurate. And I also put the computational cost here kind of at not great either. And you could debate with me on that, but linear elasticity is very hard to solve when you're getting beyond 1% strain or so. So I don't recommend it if you've got errors in your model there. It's going to increase your computational costs, and getting some plasticity in there would be very, very helpful for you. Elastic plastic models, they're really only good if you only have spec sheet data, only for plastics, and you only have monotonic loading. Overall, the computational cost is generally pretty good. It's it can be pretty easy to calibrate depending on how accurate you want to be, but I don't think the model itself is very accurate. Hyperelasticity or hyperelastic models, really, I think that those are a very good sweet spot. You get a lot of nonlinearity, but you're not getting any of those rate effects. And overall, they're a little bit easier to calibrate, and you don't even need any extra licenses. And you usually do that with test data built into Ansys. But then we start to get into really what I like to work in, and most of the models I work with are either linear viscoelastic or nonlinear viscoelastic, viscoplastic. And that's where we're really starting to get a lot of benefit capturing those nonlinear time effects, nonlinear stress strain effects, and getting that for a wide range of materials. So, please reach out if you have any questions. I see some questions here over on the right that I'm going to go back and answer them through, and I'll do that here quickly. So let's see. Yeah, TTI, we talked about that. Here, if you have an application that would potentially see 100% strain and tension, where would you cut off the test data in terms of engineering strain for the purpose of curve fitting? What would be the best practice? Well, there's going to be different best practices. So what I would do is I would probably give myself a factor of safety of 25 or 50%, meaning I'd cut the data off at 125% or 150% to make sure that I'm not getting myself in trouble. So that's what I would consider that. Someone else here says, did you calibrate the Yo model with Mullen's effect using all of 5 repeated loading and unloading test data at each strain, or did you take an average? Yes, I use each of those 5. So if we go back to, I don't know, it's around here. Kind of mentioned it when I talked about calibration. So the way we calibrate this is we do a single element simulation, and it simulates up to, I don't know what this was, 5% strain. This was a strain control test. And then it unloads to this strain, and then it unloads to 5% and unloads and does that 5 times and goes up to the next one. So it does this exact strain history repeated over and over again, because those repeats will also help you dial in some of those parameters, and particularly the R parameter, and how fast you accumulate that damage that really goes in there. Uh, our applications are all biaxial stress. Can you get reliable viscoelastic, hyperelastic, viscoplastic model from uniaxial testing? The answer is going to be it depends. Um, if you're talking about, do you say this? Uh, rubber materials generally, the finite element code manuals, including ANSYS, will tell you need to test in tension, biaxial tension, and planar tension or shear. Uh, and depending on the model you choose, that can be right. To take a step back, you can get a pressure dependence between those different loading modes, and that's why they recommend that. And there are some models that can capture that. What I have found in my experience is that that pressure effect is generally very low compared to time effects, temperature effects, things like that. And the test modes to get that data are generally much more difficult and have a higher uncertainty on them. And so generally, and it's generally a small effect. So my philosophy is normally that is going to take a lot of extra effort, and we're going to improve the model by a very small amount. So I think uniaxial tension or uniaxial compression will be plenty. Now, you won't want to use like a Mooney-Rivlin model for that, because the Mooney-Rivlin model can get yourself in trouble if you don't have the test data necessary to support that. So you want to be careful in your selection of the hyperelastic model you use, but you can. The caveat there is when we're talking about thermoplastics and we're talking about some of these plasticity models, I would recommend more than one mode, because more than one mode can be important to capture a difference in yield, in tension versus compression versus shear, and you need multiple modes for that. How many elements are used to capture the frequency range? You know, I generally use one relaxation time per decade of frequency. That can usually get me what I need, and so that's my rule of thumb. There's always going to be exceptions to that, but that's my rule of thumb. It was some sort of adhesive master curve. It might not have been a PSA. It might have been an OCA. I can't remember right now. What's the best way to check model stability in terms of mathematical check, physical meaning, and potential overfitting? So Drucker stability is what you're asking about. I believe Ansys does a check for you when you're talking about a hyperelastic model. So I believe that's output in the .out file. I'd have to check. That's generally how I do it. But to kind of the question earlier about different test modes, if you're not using like a Mooney-Rivlin model or something that uses an I2 dependence, generally you're pretty safe, and I wouldn't worry about that too much. Would these models lend themselves well to rotational cycling as in rolling contact fatigue? I don't see why not. I don't know what particular model you're talking about, but the LVE or the nonlinear, the Bergstrom-Boyce or the three network models should all capture that fine. Then there's a question: what about damage up to failure? Yeah, so none of these models include damage for failure. So I think about damage in two types of way. There's damage that modifies the material response. So like Mullen's damage does that; it softens it. That mu factor where the stiffness changes, that softens the material, but it doesn't actually lead to material failure. That's a different type of damage. I would say I wouldn't do that in Ansys Mechanical, because I will only do that in explicit simulations, and Ansys Mechanical is an implicit solver. There are ways to do it in Ansys Mechanical, but it's not something that I've spent a lot of time on. So I wouldn't, I think it's a little out of scope here. Which tests are needed to calibrate the TNM model? I would test in tension and compression, multiple strain rates in one of those modes with some cyclic loading. Can the models be hooked up to the testing in the digital twin fashion for the calibration? I think so. That's a very broad kind of question, though, so I need to know a little bit more. We are hitting time here. So I would love for those. There are a couple questions. There are a couple questions that are outstanding. I would love if those people would shoot me an email. I'd be happy to kind of answer some questions and see what I can do there. But otherwise, thank you all very much for attending. This has been great, and I've really enjoyed the interaction, the questions today. So please, thank you again for attending and this webinar. And if there are any further questions or anything else that you need, please reach out. Thank you very much.